The pump's shaft has mounted on it all the moving components of the pump. This includes the impeller, bearings, as well as various seals. The pump's shaft is connected to the shaft of the driver by means of a coupling. The three main types of couplings used on pump and driver combinations are belt couplings, rigid couplings, and flexible couplings. If an overload, such as one caused by the jamming of the impeller, were to occur, the design of the coupling should cause the coupling, and not the pump or motor shafts to fail. This is due to the fact that it is much safer for the coupling to fail, and that it is much easier and cheaper to replace the coupling than it is to replace either the pump or motor. Belt couplings fail by simply slipping on their pulleys, which can cause the belt to overheat and break within a short period of time. Rigid and flexible couplings, on the other hand, fail by fracture of some element of the coupling. Thus for rigid and flexible couplings, the coupling element that is designed to fracture when overloaded, should be weaker than the shafts of either the pump or motor. The coupling guard prevents pieces of the coupling from being projected into the pump's surroundings, in case the coupling fails. When selecting or replacing a coupling system, one has to be aware of the main requirements for the coupling. The main characteristics of a shaft coupling system are its physical dimensions, its torque rating, its speed rating, its operating temperature range, its angular misalignment compensation capability, its parallel misalignment compensation capability, its allowed axial motion, and its torsional stiffness. The main physical dimensions of a coupling system are the length of the coupling, which is important in determining whether or not the coupling will fit within the intended assembly, its bore diameter, which refers to the diameters of the shafts that the coupling is used to connect, and the maximum outside diameter. If the coupling system incorporates a keyway to connect the coupling to the shaft, the dimensions of the keyway must also be specified. The torque rating of a given coupling refers to the maximum twisting torque that can be continuously applied across the coupling without damaging it. For more information about twisting torque, click on the shown link. In SI units, the twisting torque rating is usually expressed in units of Newton meter. In English units, the twisting torque rating is usually expressed in units of foot-pound. The speed rating of a given coupling refers to the maximum speed at which the coupling can be rotated. The speed rating usually has units of rotations per minute. The operating temperature range of a given coupling refers to the temperature range in degrees Celsius or degrees Fahrenheit within which the coupling will operate reliably. The angular misalignment compensation capability of a given coupling refers to the maximum allowed angle, in degrees, between the input and output shafts. It should be noted that as the misalignment angle increases, the bending stress acting on both the input and output shafts also increases. Hence one must make sure not only that the coupling can handle the angular misalignment, but also that the input and output shafts can handle the resulting bending stress. The parallel misalignment compensation capability of a given coupling refers to the maximum allowed distance, in inches or millimeters, between the center lines of the input and output shafts. It should be noted that as the misalignment distance increases, the bending stress acting on both the input and output shafts also increases. Hence one must make sure not only that the coupling can handle the parallel misalignment, but also that the input and output shafts can handle the resulting bending stress. The axial motion limit of a given coupling refers to the maximum allowed compression or expansion displacement amount of the coupling. It is measured in units of millimeters for SI units and inches for English units. The torsional stiffness of a given coupling refers to the angular deflection, measured in degrees, of the coupling when it is subjected to a unit torque. This property is important for couplings that are used in applications where the positional accuracy is important. In pumping applications, however, accurately determining the angular position of the pump's shaft is seldom needed. In SI units, the torsional stiffness is usually expressed in units of degrees per Newton meter. In English units, the torsional stiffness is usually expressed in units of degrees per foot-pound. There are three main types of couplings that are used to connect a pump to its driver. These are belt couplings, rigid couplings, and flexible couplings. Belt-driven couplings require the pump and driver to both have pulleys attached to their shafts. The axes of the pulleys should be parallel, and both pulleys should be rotating in the same plane. To install the belt, the driver is moved towards the pump, using the jacking bolts. This allows the belt to be easily placed in the grooves on both pulleys. The driver is then moved away from the pump with the jacking bolts until the belt is under light tension. Belt-driven configurations have several advantages over other coupling methods. Due to the flexibility of the belt in belt couplings, the coupling can accommodate high values of acceleration and deceleration of the load. If the pump jams for any reason, such as debris in the suction line stopping the impeller's rotation, the belt can slip, to prevent catastrophic failure of the pump. However, if the belt continues to slip for some time, it will be worn out. Yet replacing the belt is easier and cheaper than replacing a coupling or a broken pump shaft. In most pump applications, the driver rotates at a constant speed. Belt couplings make it easy to change the speed of the pump by changing the size of the pulleys on either the pump or the driver. This allows the operator to fine-tune the speed of the pump to optimize efficiency. The belt coupling is also tolerant of pump and driver misalignment. The disadvantages of belt-driven configurations include higher maintenance requirements due to the more frequent inspections and adjustments that are needed to maintain belts. And, while direct couplings can outlive the pump and driver if they are properly installed and used, belts have a set life, after which they should be replaced. As belts near the end of their life cycle, they will stretch and loosen, causing slippage and reduced efficiency. Rigid couplings are couplings that rigidly connect the driver and driven shafts together. Their torsional strain under a torque load is comparable to the torsional strain of the shafts themselves under the same load. The main two types of rigid couplings are flange couplings and key couplings. Rigid couplings have some advantages. These include their cheap price and the fact that they require very little maintenance. The couplings must only be inspected periodically to make sure that they are properly aligned and that none of their components are getting loose. The disadvantages of rigid couplings include the following. They cannot dampen or absorb shock loading. The high torques associated with the sudden accelerations or decelerations due to shock loading are hence transferred to the pump and motor shafts. This can cause fatigue failure of the pump's shaft, seals, or other components. A second disadvantage is that in order to work properly without exerting too much load on the bearings or other components of the pump or driver, the coupling must be precisely aligned. This is especially difficult for pumps that are operated with large temperature variations of the pumped fluid. This is due to the fact that as the temperature of the fluid, and hence the pump, changes from the value at which the alignment was made, thermal expansion of the pump's components and supports will cause the pump to go out of alignment with respect to its driver. One type of rigid coupling is the flange coupling. A flange rigid coupling has a pair of flanges that are attached to the shafts using keys or set screws. The two coupling halves are then bolted together. The flange coupling should be designed so that during normal operation, the torque is transmitted through the friction that exists at the flange faces. This causes the bolts of the coupling to be subjected only to tension stress, with no shear stress during normal operation. Another type of rigid coupling is called the key-rigid coupling. The key-rigid coupling is split into two halves along a plane that contains the shaft's center line. The two halves are held together by a set of screws. The torque is transferred by means of a long key that connects the two shafts together. The top portion of the key is also inserted into a keyway in one of the halves of the coupling. Alternatively, two short keys can connect the coupling's body to the two shafts. In this case, the torque is mainly transferred by the coupling's body. Sometimes the friction due to the clamping force from the bolts that hold together the two halves of the coupling's body can be enough to transfer the torque load. Flexible couplings connect the pump and driver. They have the advantage of absorbing some of the shock transmitted from the driver to the pump on startup. They also minimize the effects of high accelerations and decelerations that can occur if debris in the pump intake momentarily slows the impeller's rotation. Flexible couplings also absorb some vibration while the pump is running. Flexible couplings allow for some angular and radial misalignment between the input and output shafts without generating high bending stresses in the shafts. The angular misalignment can be as much as 90 degrees for some flexible coupling types. Even though pumps should be properly aligned to their drivers during installation, many factors can cause a pump to go out of alignment during its operation. These include the settling of the pump's foundation, thermal expansion or contraction of the pump, its supports and the base plate when fluids of high or very low temperature flow through the pump. And lastly, forces induced on the pump from other parts of the piping system. These include pressure forces from the fluid, and movement of the intake or outlet pipes. The disadvantages of flexible couplings are that they have a higher initial cost and require more maintenance than the rigid coupling types. There are three types of flexible couplings: mechanically flexible couplings, materially flexible couplings, and couplings that are both mechanically and materially flexible. Mechanically flexible couplings rely on the relative motion between two mechanical elements to achieve flexibility in the coupling. Mechanically flexible couplings are sometimes called lubricated couplings. This is due to the fact that the relative motion that exists between the parts of the coupling requires lubrication. Mechanically flexible couplings can be divided into gear couplings, roller chain couplings, and universal couplings. A gear coupling, which is sometimes called a dental coupling, is made of two coupling halves. One coupling half is connected to the driver's shaft, and the other to the driven load. Each of the two coupling halves is connected to its shaft with a key. The outer hubs of the coupling halves are connected to each other using a set of bolts. Each coupling half has an inner sleeve and an outer hub. The inner sleeve has external gear teeth cut on its outside surface. The outer hub has internal gear teeth cut on its inside surface. A clearance fit between the inner sleeve and the outer hub creates a large amount of backlash between their teeth. The backlash movement is the source of the coupling's flexibility. The advantages of gear couplings include their ability to handle high values of torque, their ability to handle high values of speed, their intermediate ability to handle angular and parallel misalignment as compared to other flexible couplings. They are very well able to accommodate large axial shaft motions. The disadvantages of gear couplings include the fact that they require lubrication. As the transmitted torque by the gear coupling approaches the coupling's torque rating, the coupling behaves more and more like a rigid coupling. In this case, if misalignment is present, the coupling transmits a high bending torque to the pump's bearings. The inner sleeve of the gear coupling is effectively floating within the outer coupling hub, with a small clearance between them. In order to avoid vibrations due to the inner sleeve and outer hub being off-center, the coupling must always be transmitting an adequate amount of torque during its operation. The torque tends to center or pilot the inner sleeve to the outer hub. Hence, gear couplings should not be used in applications where the torque varies over a very wide range or drops to near zero values during the operation of the pump. The roller chain coupling is another type of mechanically flexible coupling. It has two coupling halves. The first half is connected to the driver motor, and the second half is connected to the driven pump. The two halves are usually connected to the input and output shafts using keys. Each of the two coupling halves has a set of sprocket teeth on its outer surface. The sprocket teeth are connected by a double roller chain. The clearance between the sprocket teeth and the roller chain is the source of flexibility in the coupling. The advantages of roller chain couplings include their ability to handle high values of torque, their relatively low price. The disadvantages of roller chain couplings include the fact that they should only be used in low-speed applications, the fact that they require lubrication, and the fair amount of noise they produce during operation. The universal joint is also known as a U-joint, a Hardy-Spicer joint, a Cardan joint, or Hooke's joint. It consists of two rotational joints that are located close to each other and oriented at 90 degrees with respect to each other. The universal joint is not able to accommodate parallel misalignment or axial movement. The universal joint is, however, able to accommodate large values of angular misalignments between the input and the output shafts. If the input and output shafts of a universal joint are not perfectly aligned with an angle of 0 degrees between them, the speed of the output shaft is not constant. As the angular misalignment increases, the variation in the speed of the output shaft increases. The speed of the output shaft, divided by the constant rotational speed of the input shaft, is equal to the cosine of the angle beta between the input and output shafts, divided by 1 minus the multiplication of the sine squared of the angle beta times the sine squared of the angle theta 1, which is the angle made by the input shaft as it rotates. Shown on the graph is the variation of the ratio of the speed of the output shaft to the speed of the input shaft, as the input shaft undergoes a full revolution from theta 1 equals 0 to theta 1 equals 360 degrees. If the two shafts are collinear, which means that beta equals 0, then W2 is equal to W1 for all values of theta1. Notice that as the angular misalignment increases from 15 degrees to 30 degrees to 45 degrees to 60 degrees, the maximum difference between the speed of the output shaft and the speed of the input shaft increases. As the output shaft accelerates and decelerates at high angular misalignments, a jerky rotation speed is passed to the driven load. For this reason, it is not recommended to use the universal joint for angular misalignments that are larger than 45 degrees. At an angular misalignment of 90 degrees, the joint locks and cannot rotate. A double universal coupling can be used to overcome some of the limitations of the single universal joint. The double universal joint is made by connecting two single U-joints. This arrangement can accommodate large angular misalignments, as well as parallel misalignments between the input and output shafts. An expansion joint can also be provided on the shaft that connects the two U-joints of the double joint. The expansion joint is usually made up of a spleened inner sleeve and a spleened outer hub. The hub and sleeve can slide on each other in the axial direction, but the spleens prevent the hub from slipping on the sleeve in rotation. The speed of the output shaft in the double universal joint is always equal to the speed of the input shaft. Double universal joints are used in many pump applications where alignment is an issue. These include applications where the pump and driver are separated by a relatively large distance of several meters. An example of such an application is the driver for a vertical submerged pump that is running much higher above the pump to protect it from being subjected to the working fluid. Double universal couplings have many advantages. These are as follows. They can accommodate large angular and parallel misalignments. If they have a centrifugal expansion joint, they can also accommodate large axial motions. The disadvantages of universal couplings include the fact that they require lubrication and more frequent inspection. Double universal couplings also require more space to be installed since they are almost twice as long as other coupling types. A double universal coupling is also more than twice as heavy as most other coupling types with the same power rating. For the same power rating, a universal double coupling is more expensive than most other coupling types.